welcome you to my lecture today. Of course, this week there's no assignment. Of course, our midterm 2 is April 17, right? So that's why there's not going to be any assignment, any discussion. I'm also going to make that announcement on the announcement section for you to have room for, to prepare for your midterm 2. Today, I'm going to finish the material we started on Friday. Of course, this is just extracted from the material on Friday, and I'm also going to walk you through midterm 2 practice questions. Now, let me tell you, the midterm 2 practice question we actually revolve around what we did in assignment 7, 8, and 9. Does that make sense? So today, I'm going to walk you through assignment 7 after finishing these. Does that make sense? Okay, now let's get started. We're going to start with sampling with T and F distribution. Before now, I think I've walked you through sampling distribution of means, maybe for one population, for two population. I also walk you through sampling distribution of proportion for one population or for two populations. I also walk you through sampling distribution of variance. But when do we use T? Maybe you want to conduct a test. When do we use because what we're gonna do after the midterm 2, we're gonna be talking about one sample T test, two sample T tests, and we're gonna be focusing on T test, Z test. Now the question is gonna come up: when do we use T? When do we use Z? When do we use F? Okay, so the focus today is I'm going to start from when do we use our T distribution. Now, as you can see, the T distribution is what I presented, which is looking, the only difference between this T distribution and the Z that we know about, the Z that we know about, okay, we have this guy. You understand that? Okay, but if you take a look at the T now, okay, the T now is still this guy. Now, if you notice the difference between them, it's just this guy and this guy, right? Now, we use Z when the population standard deviation is known, okay? Here, sigma is known. Okay, here, sigma is unknown. Okay, when sigma is unknown, what we're going to do, we're going to replace that with a sample standard deviation. Sample standard, okay, deviation. And of course, if I want to get my sample standard deviation, it is summation xi minus x bar squared divided by n minus 1, the square root of that. Okay, so the sample standard deviation is just going to replace, the one that is unknown. Does that make sense? So the idea of using the T distribution to replace the Z distribution is when the population standard deviation is unknown. Does that make sense to everyone? You see the difference, right? Okay. Now, if I have a T distribution now, okay, from a T distribution, I want to derive a new random variable. Now I'm gonna write T distribution now. The T distribution is x bar minus mu over sigma over that over this, right? If I want to write this in another way, okay, I'm basically going to do x bar minus mu over square root of s squared over n, right? Are they not the same? They are the same, right? Take a look at that. This is the same as that. Okay, if I now want to divide the ratio, okay, or probably by sigma over n, in a way, Okay, maybe I want to divide this by, I want to do like, okay, this divided by sigma over root n. Okay, and this guy also divided by sigma over root n. If I divide the entire, this guy by this and this guy by that, okay, now you're basically going to see x bar minus mu over sigma over root n, everything divided. If I put, I want to put this and this into the same square root. Okay, if I want to put them inside the same square root, if I have this guy, okay, if I want to put this into the same square root, this is going to be sigma squared. And this is going to be, so I'm actually going to have sigma squared divided by n. Right? This is not inside the square root. If I want to put it inside the square root, it will be sigma squared n. Okay? When I have that, this guy will cancel that, right? Okay? So when that guy cancels that, what do I have? Sigma squared sample variance divided by population variance, right? That's what you have over there. Sample variance divided by that. Okay. And if that is what I have, what is this guy? That's a Z, right? That's a Z, right? So this is going to be Z divided by S squared divided by sigma squared, right? If you take a look at what I actually have. Now, if you now look at the situation, the whole of this guy, okay, we can actually write the whole of that guy of sigma squared, this one divided by that, to be the same thing as V over n minus 1. Where is the n minus 1 coming from? The n minus 1 coming from the fact that, if I have this divided by this, you remember last time I said we're going to have a random variable V, which is going to be sample variance over sigma squared n minus 1. I define a new random variable as that, right? From this now. So the ratio of this is the ratio of another random variable V divided by n minus 1. The ratio of this is automatically this, statistically. Then from there, the V will now be, when I cross multiply, my V equal to this. And this guy here follow a chi-square distribution. Okay? That guy follow a chi-square distribution. Okay? Now, let me tell you this. Based on the fact that I actually, based on the fact that, based on that, I can rewrite this guy. I can write Z. I can write that T equals Z divided by V over R. Oh, sorry, V over small v, where this guy is the degree of freedom. And this very V, this guy is standard normal variate, and this guy V, okay, it follows a chi-square. Okay, it's a chi-square variance with a degree of freedom, this guy. Now, it means the way with a T distribution was derived using the ratio of a standard normal variate to the square root of a chi-square variate divided by the degree of freedom. And that's, if we follow what we've done before on the Jacobian transformation, is going to end up is in this. This is what we call T distribution. For this one, if I want to do that, it's going to take forever, but it can be done. I want to go from variable V and Z to T, right? I need to create an artificial variable, maybe W, and I'm going to equate that W to maybe to V. Okay. Now I need, what I want to finally get is G of T. But to get it, which is going to be this guy here, to get the G of T, I need to, for of us, what is Z? Z follow normal with 0 and 1, which is going to be f of z equal 1 over square root of 2 pi exponential raised by this z squared. Z follow that. Then V follow chi squared. V follow chi squared with V degree of freedom, where the f of V will be V raised to power minus with big V raised to power let me see if I have that is V2 V over 2 minus 1 exponential raised to power V over 2 gamma V over 2 raised to power V over 2. If you could take a look at what we've done before in the chi-square, and of course because Z and V are independent, I four of us need to get the joint of T and V, which is going to be f of Z multiplied by f of V. We are multiplying that by that, and after doing that, I need to set up my Jacobian. Okay, based on what we've done before, I need to set up my Jacobian. But you know what? I'm not going to ask you to prove that. Okay, I'm not going to ask you to prove. I'm just trying to. So if I set up my Jacobian transformation, I need to express V in time. So here now, V equal to W, and I need to get my Z. Okay, so Z equal T square root of W over small v, because this V here is W. So where I can do the W, the V, the W, the T, then I can also do the Z, the V, and then the Z, the T, where I'm going to get my Jacobian, and in the end, I'm actually, so because when I obtain the G of Z, the G of Z and V, and in the end, I'm actually going to get the G of T, the G of T, and the W that and the V that I created. Okay, so that when I plug in, then I'm going to multiply by absolute value of Jacobian. You know what we've done before, but you don't need that. Okay, but I'm just trying to tell you, what is the essence? The ratio of a random variable that follows standard normal distribution and a V that follow chi-squared, that will lead to the distribution of the T. Now, what is the essence of the distribution here? This is what we use to simulate values in the T table. When you look at the range of T from negative infinity to infinity, okay, with small v as the degree of freedom, that was what we used to simulate values that you always check in the T table. Okay, now this is a corollary. If I have a random variable x1 up to xn, they are independent. We can find the mean, we can find the sample variance. Okay, and if we get the mean, the sample variance, with the sample variance, even if the population is on the population standard deviation is unknown, we can use the idea of sample variance. When you find the square root of sample variance, what does that give you? Sample standard deviation. And with that, we can use our T distribution, because the T distribution requires that even though we don't have the knowledge of population standard deviation, we can use sample standard deviation in replace of that. Okay, now the next thing is just go to the table. You're going to be checking something from the table now. I just showed you what we use, because some of you may be wondering. I remember when I was in high school, or when I was in college, I normally ask the values we're checking from statistical table. Where do they come from? They actually come from distribution. I just told you now. Okay, now the T value with V equal to 14 degree of freedom, that leaves an area of 0.05 to the left, and therefore if you leave an area of 0.025 to the left, automatically to the right will be 1 minus 0.025, which is going to be 0.975 to the right. Does that make sense? Because the total area under a curve must be equal to 1. Does that make sense? So if I want to check that, the t is 0.975 will be exactly the same as the negative t of 0.025. That would be negative 2.145. Where do I get 2.145 from? I check that from the t table under the degree of freedom 14. Do you know the same way we ask a question that has to do with checking from z table, we can also ask question, checking from t table. Or if they ask you to find the probability of a t lying between negative t of 0.025 and 0.05. Okay, this is the analysis. In the end, I got a 0.925. I check all that from the table. Does that make sense? So we're making use of that table now. Okay, now when I talk about the distribution, this is exactly what I mean. Okay, now find k such that the probability of t lying between k and negative or minus 1.761 equal to 0.045. This time around, we actually want to figure out the lower bound. We know the upper bound. The upper bound is negative 1.761. We don't know the lower bound, but we know the probability. We know the area, between the unknown lower bound k and the negative 1.761. Okay, now you can even indicate that from using it, by sketching the curve. When you sketch the curve, okay, if you take a look at that area, is 0.0045, okay, and you can see the center. The center is actually 0. Let me tell you that the center of a t distribution is also 0. The same as the center of his standardized normal variance. Okay, so if you now want to check now, okay, you need to go to the body of the table. Okay, where can you see 1.761? Under what degree of freedom? Oh, I found that under the degree of freedom 14. Okay, and that was why I said the t negative aspect of that would be negative 1.761. Okay, and in the end, I can actually, and I know that I have a 0.045, then I'm going to say 0.045 equal to 0.05 minus alpha. I got that. Then I can figure out my k. Okay, I can actually do that. Take a look at that. Any question? Any question? Okay. Now, we want to go into an example now. A chemical engineer claims the population mean yield of a certain batch process is 500 grams, okay, per millimeter of raw material. Okay, to check this claim, a sample 25 batches each month. If the computed t-value fall between that and that, okay, it is satisfied with this claim. Let me tell you this. If investigation always follow a claim, whenever there's a claim, okay, investigation will follow that. Okay, when we are investigating, you're going to take a sample, right? Okay, so what conclusion should be drawn from a sample that has a mean of 518 grams per milliliter and the sample standard deviation? Look at that. You are giving sample standard deviation. You don't have a population standard deviation, and that should suggest to you you're basically going to use a t distribution. Does that make sense? Okay. Now, what you want to do now is you can check all those ones from the table. You know your sample size to be 25. The degree of freedom will be sample size minus 1. That will be 24, right? So 24 degree of freedom, okay? 24 degree of freedom with the 0.05, that will give you 1.7111, okay? Now, if that gives you 1.711, if you want to figure out your t, now 518 minus the mean, the population mean, the hypothesized mean, 500 divided by the standard deviation is 40. Okay, you've been given standard deviation divided by the square root of 25. Your t will be 2.25. Okay, now when you have a 2.25, the calculated t is greater than the t you check from the table. There's a difference between the calculated T and a tabulated T. I'm going to say that again. There's a difference between a calculated T and a tabulated T. The calculated T is the one you compute yourself using the T formula. Then the tabulated T is the one you check from the table of T, okay, with a given degree of freedom. And as you can see, the calculated T is greater than the tabulated T. Now, let me tell you this. We normally use two ways to take a decision regarding an hypothesis. When the calculated statistic is greater than tabulated, we're going to reject H naught. We are rejecting the claim. We are rejecting the non-hypothesis. In an hypothesis testing that we're still going to do, we're going to have two forms of hypothesis. We're going to have the non, which is HO, and the alternative. Okay, the non is going to say, oh, it is 500. The alternative now is going to say it is more than 500. It's similar to what we did in a law court, where they're going to say an accused person is innocent, and the alternative is going to be accused person is guilty. So here we are testing that the mean is 500 against that the mean is greater than 500. And we're actually going to compare the calculated T with the tabulated T. When the calculated T is greater than the tabulated T, then we're actually going to reject. This is what happened. Now, this is what happened. HO is mu equal to 500. HA is mu greater than 500. This is a non-hypothesis. Okay, and this is the alternative. Now, the claim, if you take a look at that, a chemical engineer claimed that the population mean yield of a certain batch process is 500. That is it. This is under a claim now. And we now say, no, it's going to be, maybe it's going to be greater than that. This is under hypothesis. And for us to take a decision now, we're actually going to compare the T calculated with the T tabulated, and the decision rule is if T calculated, if it is greater than T tabulated, reject HO. Otherwise, do not reject. But right now, the T calculated 2.25 is greater than 1.711, and that was why I said the probability of attaining a T value with T equal to or greater than that is approximately 0.02. So if I can take decision here using this, or I can also take decision with a P value. I need to calculate. The P value is going to be, what is the probability of a T greater than, what do I get? 2.25. If I want to get a probability, that probability was what we found to be 0.02. And let me tell you, I said there are two ways of taking decision. One, it said that you can reject H naught if T car greater than that, or when the P value is less than alpha. When P value is less than alpha, what is alpha? Alpha is the level of significance. We should call it 0, which is 0.05. Now take a look at that. The 0.02 is less than the 0.05. Okay, we're also going to reject. So there are two ways we can take a decision. It's either we compare the calculated with the tabulated. If the calculated is greater than the tabulated, we're rejecting the H naught. And if you want to use a p-value, if the p-value is less than alpha, the level of significance, we reject a show. And that's exactly what we're trying. So what I'm trying to say, and the engineer is likely to conclude that the process produces a better product than he thought. What was his thinking? His thinking is 500, but we've rejected that based on the empirical evidence. We are here now. This is where we are now. Then it is greater than what he thought. Any question? Okay. I think I've just I've mentioned what is useful, but let me tell you this: whether the only difference between the Z and the T is when the population standard deviation is given or not. When the population standard deviation is known, we go for Z. When it's unknown, we go for T. But the facts remain that we are still going to be working with the normal population. If the population is not normal, then the central limit theorem must apply for both. Okay, where the sample size have to be at least 30. Okay, now the last thing I'm going to talk about is F distribution. There's a lot of story to arrive at this distribution. Let me tell you this: F distribution was derived as a as a result of the ratio of two independent chi-square. Okay, when you follow chi-squared with V1 degree of freedom and V follow chi-squared with U2 degree of freedom, the ratio of that, if I want to go by Jacobian transformation, going from 2 to 2, I'm actually going to arrive in this distribution F. Do you know that this is a formula they use to simulate data in the F table when you check statistical table? Now, what do you think is going to take me to checking from F table? Maybe I'm doing an ANOVA test. Has anybody heard about ANOVA test, where you are comparing means in more than two population? Okay, we're basically going to use F test. When you are using F test, you are using F distribution. Okay, and F distribution come with two different degree of freedom. That's why you see V1, V2. Okay, if I want to check for a values under F distribution, okay, I can check under degree, okay, like 6 degree of freedom, 10 degree of freedom, then I'm going to have a value. And what I'm trying to say here, 6 degree of freedom, 10 degree of freedom, if I switch that, if I switch the degree of freedom, okay, it's the same thing as the 1 over that is the same thing as that. So if you are checking from F distribution, you're basically going to use 2 different degree of freedom. Okay, and what are you comparing when you do that? Maybe you are comparing means in more than 2 populations. We have a more than two groups, independent groups, and I want to investigate whether mean is the same. If I want to investigate whether mean is the same, I will be analyzing the variances. I'm going to say that again. When I'm testing for equality of means in more than 2 populations, I will be analyzing variance. And that is why it is called analysis of variance. In analysis of variance, we are testing the quality of means. If I basically want to take a decision, I need an F distribution. We're going to talk about this later. Okay. This is where I'm actually going to stop. And I will quickly share the practice question. Give me 1 second. Okay. There's a few. Let me see. Okay, I think there's nobody online this time around. Okay, now I want to welcome you to midterm 2 preview. You know what we're going to be doing from now till Friday? What we're going to be doing from now till what? Till Friday is to walk you through assignment 7, 8, and 9. You know why? Because the area covered in assignment 7, 8, and 9, okay, will be the area that will be covered in the midterm 2. Don't forget, the midterm 2 is April 17. Okay, and that was why I said the assignment 7, 8, 9 actually covered chapter 5, chapter 6, chapter 7. The midterm 2 is only going to cover chapter 5, 6, and 7. Does that make sense? No chapter 8. Does that make sense? We just finished chapter 8 now. And I want you to focus on your assignment. That's why the solutions are already uploaded, but I'm going to go over that with you in class now. I'm basically going to start with problem 5.5. Let me tell you this. When you are given a question under discrete, we may not tell you it follow a particular distribution in the discrete, but when you are given under continuous, of course, we're going to tell you. So you should be the one that will be able to figure out what kind of distribution. Now take a look at question 5.5. This was, you can find this in the assignment, right? According to chemical engineering process, November 1990, approximately 30% of all pipe work failure in chemical plants are caused by operator error. What is the probability that out of the next 20 pipe work failure, at least 10 are due to operator error? And they also ask other question. Now, when you take a look at this, it's either you have operation error or not, right? That makes it binomial. Does that make sense? That makes that to be binomial. Now, if it is binomial, since I'm actually going to, what I need you to do, right? When you want to call me with a sheet, why not writing all the probability distribution formula on your sheet? Like for instance, I know this question is going to be coming from binomial. Okay, it's going to be coming from binomial. Now, if it is coming from binomial, of course, x follow binomial with a parameter n and p. Okay, now that's going to be the probability of that is a combination s, p raised to power x, 1 minus p raised to power n minus x. Let's start from 0, 1, 2 until I get to n. Now I'm going to look at this question now. What is my n? Oh, my n is 20. Because if you look at the question, my n is going to be 20. What is my p? Because it said 30% of pipe work failure. That is the probability of the characteristics of interest here now, which is going to be 0.3, right? Now the first question now said, what is the probability that out of the next 20 failure, at least 10? Oh my God. When you take a look at A, at least, I want you to pay attention to some words. Exactly 10, at least 10, at most 10, less than 10, greater than 10. They are not the same. When I say at least 10 now, you actually want to find this. It means the minimum is 10. 10 and above, that's what it means. Now, and if you want to do 10 and above, if you look at the state space of binomial, it goes all the way. It means 10 and above, I'm going to go all the way to 20. I'm going to do 10. I'm going to find the probability of s equal to 10 using the formula s equal to 11, s equal to 12. That would be a lot. But another way is 1 minus the opposite of this guy. What is the opposite of that guy, right? If greater or equal, that should be less than 10, right? And when I want to talk about less than 10, that would be 0 to 9. Okay, so in 0 to 9, I'm going to have 10 of that. 10 to 20, I'm going to have 11 of that. It now depends on you, how you want to go. So here now is 1 minus the probability of x less or equal to 9, which means I'm actually going to do 0 for 0 for this one. It's going to be for 0, for 1, for 2 up to 9. I'm going to be using the formula here, plugging in n to be 20 and p to be 0.3. Who doesn't understand how to do that? Who doesn't understand how to do that? Okay, which means everybody understand that. Now the next question says, what is the probability that no more than 4? No more than 4 is sitting at most 4, which is probability of x less or equal to 4. That is what that guy means. No more than 4. No more than 4. It can be 4 or less. That's what it means. No more than 4. Okay. So no more than 4. Okay, for B now, the probability of s less or equal to 4. So which is going to be s equal to 0, s equal to 1, x equal to 2, okay, s equal to 3, and X equal to 4. That is what it means. Okay. So, when you do that, of course, the solution is already provided. I'm just trying to shed more light in case there's anybody who need the clarification on that. Is there anybody who need clarification on that? Okay. Now, the next question now says, suppose for a particular plant, okay, the out of the random sample of 20 such failure, exactly, 5. That would be super easy. Exactly 5 just means you want to find the probability of S equal to 5. Okay, exactly 5. So 20 combination 5. Okay, so when you do 20 combination 5, okay, 0.3 raised to power 5, is 0.7 raised to power 15. Okay, so you're actually going to figure that out. Okay, now the question now actually come from binomial distribution. The question now, this is question 5.5 in the assignment, in assignment 7. Any question? Any question? Because in this exam, they may not be make up for midterm 2 because we're very close to the final. And that's why you have to make sure you put in your best. And that's why I'm, only limiting the questions to area covers in chapter 5, 6, and 7. And I want the minimum score in the midterm to be 99. That's possible, right? Oh, then I'm going to be celebrating. If that happens, I'm going to be celebrating, which I know is possible because you guys are smart. I know it's possible. Now, I want to go into the next question now. Okay. I want to go into the next question now. Okay. The next question is question 5.20. Okay. According to USA Today, okay, March 18, 1997, of 4 million workers in the general workforce, 5.8% tested positive for drug. Of those testing, now we're interested in those who test positive, and and they say of those testing positive, 22.5% were cocaine users, and 54.4 marijuana users. Okay. Now, if I were you, you can see, let's say cocaine users, marijuana users, or for the cocaine users, you got 22.5%. Okay, for marijuana, 54.4%. Then you should know that there's going to be others. Why others? Because this didn't add up to 100%. Does that make sense? There's going to be others. So if you add this to this and you subtract from 100, maybe you're basically going to have 23.1%. 23.1%, right? Okay, so now, what is the probability that 10 of workers, okay, testing positive, 2 are cocaine, 5 are marijuana, and 3 are others? That is more than 2 outcome. Okay, that is more than 2 outcome. That's you can't use binomial anymore, but you're going to use a multinomial. Does that make sense? Because you got more than 2 possible outcome. Even though you get more than 2 possible outcome. So if you want to answer that question here now, so you got 10 of them, 2, 5, 3. Okay, then because we're focusing on, if you take a look at that, it said 5, 3, and 2. You can see 2, 5, 3, which means 2 are for. So if you take a look at the guy now, this guy is more or less like this, and others, right? Now, this is the general one, right? Okay, then I need a probability for each of that. So the probability for each of that, okay, which is going to, the probability for cocaine is this guy here, and that is going to carry the number cocaine, right? So it's going to be 2. So I'm actually going to have for the other as well. So I'm actually going to have this. Oh my God, this is super easy. The probability for cocaine carry the number for cocaine. The probability for marijuana carry the numbers for marijuana. The probability for others carry the numbers for others. All what I just need to do here is just to compute that. That is super easy. or if it's not super easy for you, and I want to hear from you. Do you need any clarification? You are fine, right? Okay, we got 10 more minutes, right?